start. The topic of today's lecture is cross section, and it is completely conceptual. Therefore, try to understand it. And if you have any question, you can stop me anywhere. Okay? So, in a scattering experiment, one performs a scattering of one particle from the other. In a scattering experiment, one performs a scattering of one particle from the other. Okay? You can perform experiment in lab frame, or you can perform experiment in center of mass frame. Okay? You can perform experiment in the lab frame, or you can perform in the center of mass frame.
Sir, it means from the perspective of both one of the both particles.
Let me just tell you, I'm going to explain it. Now, what happens in the laboratory frame? Suppose I'm talking about scattering of electrons from the protons. Okay? I'm not telling you what are the final states. Suppose if I am talking about first, electron and proton are in the initial state, and electron and proton are in the final state. Then this scattering is known as elastic scattering. Okay? When your initial state and the final state, they are the same, then the scattering is known as elastic scattering. But you can have this process where in the final state, besides electron and proton, you can have a pi 0. Yeah, electron and proton, you can have a pi plus pi minus, or many other particles in the final state, keeping lepton number conservation and baryon number conservation in mind. Okay, these processes are known as inelastic scattering, where in the final state you have different particles. Even you can have an electron plus neutron plus pi plus. You are conserving baryon number as well as you are conserving electron lepton number. Besides that, charge is getting conserved when a pi plus gets emitted. This is also an elastic scattering. Okay. Now in the lab frame, one guy is at rest. Okay. There are two particles in the initial state, and one guy is at rest. Say, in general, I'm talking about an electron with an initial momentum k. The proton's initial momentum is p. This has got initial momentum after scattering k prime, and this has got initial momentum p prime. These are the four momentum of the particles. Therefore, four momentum includes energy part, zeroth component will give you energy part, and the 3 component will give you the 3 momentum part. Therefore, in any process, if you have K plus P as the 4 momenta of the initial state, then that means that would be equal to K prime P prime, the 4 momenta of the final state. Okay, this, what I am telling you, this will include the 0th component, and the 0th component is nothing but energy of the incident electron, energy of the incident proton, and that will be equal to energy of the outgoing electron and energy of the outgoing proton. This leads to energy conservation. And then the 3 momentum of the electron plus 3 momentum of the proton, this is equal to the 3 momentum of the outgoing electron and the 3 momentum of the outgoing proton, and this gives you 3 momentum conservation. Therefore, when we write like this is what we call 4 momentum conservation. That includes energy conservation as well as 3 momentum conservation. Now, if you have n number of particles in the final state, then K plus P will be equal to, say, P1 plus P2 plus P3 plus Pn for the n number of particles in the final state. But no matter how many particles are there in the final state, always energy and momentum will be conserved. This will be true whether we are performing experiment in lab frame or we are performing experiment in the center of mass frame. Okay?
Excuse me, sir.
Yes?
So this 4 momentum is the same as that of Einstein theory.
What is Einstein theory?
Means when
This is basically when have you been taught 4 vectors?
yes, sir. In the Griffith, it is mentioned. Griffith
4 vector is represented by, 4 vector is represented by, say, A, which has component A0 and component vector A. Okay, then in general you write it as in the contravariant and covariant form. That
Yes,
gives
sir.
you A square, and one is A0A and another is A0 minus A. Okay, contravariant is with a plus sign, covariant is with a minus sign, such that this is equal to A0 square minus A vector square. That means if I am writing it as P mu, that will be equal to P square, and that will be equal to, following this analogy, P0 square minus P vector square. And P0 square, what I am telling you, for the 4 vector, this is the energy square and this is the momentum square. Okay, and Einstein's energy mass relation tells us that E square is equal to P square plus M square, where I am working in natural units, therefore never I will write C, otherwise it is E square equal to P square C square plus M square C4. As you can notice, E square minus P square from this part will be how much? M square. Therefore, 4 momentum square of a particle involved in the scattering is equal to mass square. Is it clear?
Yes, sir.
Is there any other question? Now see what I was talking about. I was talking about a proton which is at rest. In lab frame, one guy is at rest and another fellow comes with energy and momentum. Now the guy which is at rest, what will be his three momenta? Zero. Therefore, three momenta of the particle will be zero. What will be its energy, the zeroth component or the energy? Let us call it by the name EP. What will be EP? When momentum is zero, energy will be equal to just its
M square.
rest mass. No, E square will be m square. EP will be equal to m. Okay, rest mass of the particle. Okay. Now let me just go to next slide, and that will make the things clear. What I am telling you, that there is one guy, let us call it proton, which is at rest. That happens in the laboratory frame, where EP is equal to m and P is equal to 0, and then an electron comes with certain energy and three moments. This particle is known as projectile. Therefore, you have a projectile and you have a target. Okay, you have a projectile and you have a target. Okay, therefore, the target is at rest in lab frame and its energy is rest mass and three momenta is zero, while the projectile is coming with certain energy and momentum. Now the scattering takes place. Now in physics, scattering does not mean head-on collision. Scattering means the particle feels the presence of the potential. Okay, for example, if it is positively charged, the electron will be attracted towards it. Had it been a positron as a projectile, the positron will feel the repulsive force and it will move in some other direction. And while the target is sitting over here, say, if it is lead, then this positron will feel a larger force. Okay, and we will say that scattering has taken place because we have a minimum distance of approach, and this minimum distance of approach, the particle is feeling the presence of the potential, and the particle is changing, is modulating its path. And if the particle is modulating its path, then we say that scattering has taken place. Okay, therefore here also, this was the original path of the electron. This is straight line. But because this proton was present and scattering has taken place, now the electron is moving in some other direction with energy E prime and three momentum K prime. And this difference in energy is transferred to the target, EE minus EE prime. This is the difference in energy transferred to the target. Okay, generally we write by Q0. This is known as energy transferred to the target. And vector Q, that is the momentum transfer to the target. Now see, K is the incoming momentum of the electron, K prime is the outgoing momentum of the electron. Therefore, the momentum which has got transferred is K minus K prime. Okay, and that is why we define 4 momentum transfer as Q, which has component, the 0th component, which is again the energy component, which is equal to E minus E prime, and 3 momentum component, K minus K prime. Okay, therefore you have the energy transfer to the target, you have the 3 momentum transfer to the target. Now initially the target was at rest, but when it has got energy or it has got momenta, therefore the final momenta of the outgoing particle, say this proton, is it has got energy component EP prime. How much is that? From energy momentum conservation, EE plus EP, this is equal to E prime plus EP prime, and this implies that EE plus the initially the target was at rest, this is EE prime plus EP prime. Therefore EP prime is nothing but EE minus EE prime plus M, and that is equal to Q0 plus M. This is the, if you want to be specific, you can say that this is the mass of the target particle. But I think, explicitly mentioned that M is the mass of the proton or mass of the target particle. Therefore, EP prime is Q0 plus MT. This will be energy transferred to the target. And therefore, we say that this particle has recoiled, has moved in some direction. But why we say it's recoiled? But because in comparison to electron, proton is almost 1836 times heavier. And therefore, its kinetic energy will be much smaller. And therefore, we say that this particle has recoiled. Okay, but it has moved certainly from its original position. Now, the angle that this outgoing electron makes with its original direction is known as the lab scattering angle. The angle that the outgoing electron makes with its original direction is known as lab scattering angle. Therefore, in some of the books, you will even find something like this. Okay, E electron has come, and after scattering, therefore, why I am not writing anything over here? This is because in physics, we never say that two particles have collided. What I am telling you, a particle has felt the presence of the potential. And then what happens here, since electron, proton, both are charged particles, we are talking about electromagnetic interaction. Therefore, here what is happening actually, the electron is a source of virtual photon. When electron has emitted a virtual photon, it has gone in some other direction, and that virtual photon has got absorbed by the proton, and proton is moving in some other direction. Therefore, this virtual photon is carrying a 4 momenta where it has the energy transferred component and it has got the 3 momentum transferred component. And that this EP prime is equal to Q0 plus MT, which I am writing. You may also write it as square root Q square plus MT square. Square root Q square plus MT square. Okay? And this will be true for any A plus B in the initial state. Just instead of electron, you call it by the name A, and instead of proton, you call it by the name B. Then you have A and B in the initial state, and then you can have n number of particles in the final state. That depends upon, for sure, the threshold energy of the reaction, about which we shall talk about. But in the laboratory frame, one guy is at rest and another guy comes with certain energy and momentum. Okay, the incident particle or the projectile emits a virtual photon in the case of electromagnetic interaction, W or Z bosons in the case of weak interaction, gluons in the case of a strong interaction, and moves in some other direction. And this, the virtual quanta actually gets absorbed by the target particle, and we say that scattering has taken place. Okay, therefore the important point is that if I talk about q is equal to k minus k prime as the 4 momentum transfer, then what is q square? The 4 momentum transfer square. This will be equal to k square plus k prime square minus 2k dot k prime. This q is the 4 momentum carried by the virtual photon, and this is not on shell particle. This is, although the mass of the virtual photon is mass of the photon is 0. Therefore, in general, its 4 momentum square must be equal to 0. But this is not a real photon. This is a virtual photon, and this is the difference between on shell particle and off shell particle. In the case of on shell particle, the momentum square is equal to mass square, and for off shell particle, this p square will not be equal to ms. Okay, therefore this q square is k square plus k prime square minus 2k dot k prime. What is q square then? K square is the mass of electron square plus mass of electron square. This will be 2 times mass of electron square. Then a minus sign, 2 outside. This is k0 prime minus k dot 2 me square minus, now this k dot k prime is k0 prime minus k dot k prime. Okay, that means this is equal to twice me square minus twice ee prime plus, see here, this is this is prime. Because of these two minus signs, this will become plus 2k dot k prime. And what is k dot k prime? Mod of k times mod of k prime times the cosine of the angle between the initial electron and the final outgoing electron. This is the lab scattering angle, cos theta L. Therefore, this is 2me square minus 2 prime plus 2 k prime cos theta L. Okay, is it clear? Therefore, the 4 momentum
Sir, here K and K prime are 3 vectors.
Yes, that is why this, if you wish, I can rewrite it. I am writing it here for the same 2me square minus 2 prime plus 2 square minus me square prime square minus me square cos theta. Okay.
Yes, sir.
Now, if I say that the incident energy of the what is the mass of electron? 0.5 MeV. If the incident energy of the electron is say 200 MeV or even 100 MeV, then E square is a much larger quantity than Me square. Therefore, 100 in comparison to 100 MeV, these mass of part of the electron is negligible. It will be effective only when your energy of the incident particle is say less than 10 MeV. Therefore, if the energy is say 100 MeV or the energy is 200 MeV, then this Q square, as you can see, 2 Me square I can delete. This Me square I can delete. Then this will become with a plus sign 2 E prime cosine theta. And then we have a minus 2 E prime cos E prime. If I take minus 2 E prime common, this will become how much? For the energy, which is much larger than the rest mass of the incident particle. This Q square is nothing but minus 4 E prime sine square theta L by 2. Because when you will take minus 2 E prime common, you have 1 minus cosine theta L, and that will give you minus 4 E prime sine square theta L by 2. Okay? Therefore, in lab frame, you have to understand that one guy is at rest and another fellow comes with energy and momentum. The energy is transferred, the three momentum is transferred to the target particle, and therefore the target particle recoils, and the energy of the outgoing electron is always smaller than or equal to. Now the question is when it will be equal to. The answer to that is when theta lab is 0, then you can see that this Q square will be equal to 0. Okay, that means for exact, and when theta lab is 0, then that means we are talking about exactly the forward scattering, and forward scattering means that there is no energy transfer to the target. Okay, if there is no energy transfer to the target, then only E will be equal to E prime. Otherwise, E prime, outgoing energy of the electron, will always be smaller than the incoming energy of the electron. Therefore, this E prime is less than or equal to E, and it will be equal to E only when there will be forward scattering angle. E will be equal to E prime only at the cost when theta lab will be equal to 0. Is it clear?
Yes, sir.
Mahak, do you have any question? You joined late?
No, sir.
No. Now let me change the slide. Now let us talk about center of mass frame. What happens in center of mass frame? Okay, like the experiment which is going on at LSC, Large Hadron Collider in CERN. Okay, now here what happens, that two particles come exactly from opposite direction. That means here now electron and
Excuse
proton.
me, sir.
Yes.
Sir, it's a silly question, but in the previous slide, what is the final answer?
There
I
is no
missed it. Sorry, sir, but
and see, there was no final answer. There was no question. What I was trying to describe was that what is a lab frame and how you visualize the different kinematical quantities that is involved in the lab frame. Similarly, here I am going to talk about what is a center of mass frame or what is a center of mass experiment, and how here we visualize the different kinematical quantities. Because when we will talk about the cross section, there I will directly use these results, these
Yes,
kinematical
sir.
variables. Okay,
Yes, sir.
because
Yes.
these what I thought that perhaps a few of you might be missing these important concept. That is why I have not directly started the concept of cross section. Just this has already been taught to you in BSc final. But just for a few students, I don't know whether all of you understand everything or not. Um, Before coming to this class, that is why I am repeating it. I am sorry for those who already know these concepts. Okay. Now, what happens in center of mass frame? That two particles, they approach exactly from the opposite direction. That means angle is 180 degrees. Okay, and the three momenta of the particles, the magnitude of the three momenta of the particles are exactly the same. That means if say this is k and this is, again let me write something to distinguish it here. This is k center of mass, this is the four momenta p center of mass. Okay, now what happens in laboratory frame, that k plus p, this is equal to 0. Sum of the three momenta is 0, such that k center of mass is equal to minus of p center of mass, which would imply that the magnitude of the momenta of the particles involved in the scattering, they are the same. See, I am talking about magnitude of the three momenta of the particles, they are the same. But magnitude of the three momenta, if they are the same, that does not mean the energy of the particle would be the same, because this has got mass me and this has got mass mp, and energy for the particle electron, that will be equal to kcm square plus me square, and pcm will be pcm square plus mp square. Therefore, energy is different, but the three momenta of the particles, the magnitude of the three momenta are the same. And then scattering has taken place. They have moved in some direction. Now the final momenta is kc prime. This is pcm prime. Okay. Then the same is true, because see, the three momenta has to be conserved. Then that means kcm prime plus pcm prime. Here this is again 0, such that kcm prime is equal to pcm prime. And again you can see that the energy of the outgoing electron and proton would be different, but the three momenta of the particles would be the three momentum of the particle would be the same. Therefore, in center of mass, both the particles are in motion, both the particles come from the opposite direction. And for example, what is happening at LHC? They are colliding two protons. They are colliding proton with a lead nucleus. They are colliding lead with a lead. Now, when they are colliding proton with a proton, not only the three momenta would be the same, but energy also would be the same because the masses for the two protons are the same. Therefore, in general, we say that the three momenta, the magnitude is the same, but if the particles are identical, or one is particle and another is an anti-particle. For example, if this is an electron, this is a positron, this is a proton, this is an anti-proton, and then we are performing colliding beam experiment. Okay, then in this case, the magnitude of the moment uh, what I was discussing the center of mass frame where two particles were coming from the opposite direction. And what I was telling you, that if had this been an electron and a positron, or a proton and an antiproton, then the not only the three momenta of the particles would be the same, but energy would also be the same. For example, presently we are told that the energy that is involved at LSC, we are performing experiment. What they say, claim that we are performing experiment at 14 TeV, and this is an important concept which everybody should understand. When they say that they are performing experiment with 14 TeV, that means simply that 7 TeV is the energy of one particle and 7 TeV is the energy of the other particle, and then these two particles are colliding such that the total energy of the system is 14 TeV. 7 TeV for one and 7 TeV for other. Okay, and you know that TeV is trillion electron volts, 10 power 12 electron volts. Therefore, in comparison to 10 power 12 electron volts, or in comparison to trillion electron volts, million is also negligible. Okay, therefore these proton masses you can ignore. Just what they have got kinetic energies. Okay, therefore 7 TeV is for the one particle and 7 TeV for the other particle. Now this we represent it by the symbol as 14 TeV. This we call it as, sometimes you will find in the books, W, sometimes square root S. This is we call it as center of mass energy. And try to understand what is this center of mass energy. We define a quantity S. This is equal to sum of the four momenta of the square of the four momenta of the initial particles. And since in any energy momentum conservation, if you have say A plus B are the initial particles and 1 plus 2 plus 3 plus dot n plus n are the final particles. I don't know how many particles would be produced. How many would be produced, that threshold energy will tell us. But S is Pa plus Pb whole square, and that will be equal to, by momentum conservation, P1 plus P2 plus Pn whole square. Okay, S is equal to Pa plus Pb whole square, and that will be equal to P1 plus P2 plus Pn whole square, because for momentum conservation tells us that Pa plus Pb must be equal to P1 plus P2 plus P3 plus Pn. Okay. Now, when I am talking about 4 momentum square, then that means I am concentrating in this middle term, this will be Pa plus Pb, the zeroth component square, minus Pa plus Pb, the 3 component square. Okay? Is it clear to everybody?
Yes, sir.
Okay. Now you see what happens in center of mass frame for Pa plus Pb. What I have told you, that for center of mass frame, Pa plus Pb is how much?
0.
0. Then that means, and similarly that will be true for P1 plus P2 plus Pn whole square. Okay, that the vectors part will be 0. Then that means what we are left with is the energy part, and this we call by the name center of mass energy square. The energy of the particle A and the energy of the particle B is square, and that is why square root S is nothing but E center of mass. Square root S is nothing but E center of mass. Is it clear?
Sir.
Now, what will happen in laboratory frame? In laboratory frame, this S will be equal to, tell me, here this will be EA plus, since in laboratory frame particle B is at rest, therefore the energy of the particle B will be just its rest mass. This is a square minus, here this guy is at rest, therefore you have only Pa square. Okay, and that means this S is Ea square plus Mb square plus twice Mb Ea minus Pa square. And then Ea square minus Pa square is how much? Ma square. Therefore, S is Ma square plus Mb square plus twice Mbe. Is it clear? S is Ma square plus Mb square plus twice Mbe. This will be this we call it as, this is also we will call it as the center of mass energy. That what is the center of mass energy available in the laboratory frame? We will say that the center of mass energy available in the laboratory frame will be Ma square plus Mb square plus twice Mbe square root. Now there is an important catch which I am telling you, that you perform experiment in lab frame, you perform experiment in center of mass frame. Now LHC or the modern accelerators, at the modern accelerators, generally the experiments are being performed in the center of mass frame. Okay, why is that? Why the experiments in the laboratories are performed in the center of mass frame instead of lab frame? See here and try to understand this. This is very important concept. What I am telling you, that at LHC presently the energy that they are talking about is 14 TeV, 14 trillion electron volts, and of this 14, 7 is being carried by one particle and 7 TeV is being carried by the other particle, and 7 TeV and 7 TeV from the opposite direction they are coming, and that is making 14 TeV. Okay, Now suppose I want to do the same kind of experiment in laboratory frame where I want to keep one particle at rest and the other particle I will give whatever energy is required to have a center of mass energy 14 TeV. Okay? Suppose these two particles are protons and I want that one proton should stay at rest and another proton should come with whatever energy and momenta required to have this much 14 TeV of total center of mass energy. Okay? Now I will come back to this guy, my S. That means I want square root S to be 14 TeV. That means how much will be S? 14 TeV square. Okay? This will be, I am considering proton, try to understand this. MA square. MA square means 938 MeV. If I want to make GeV, this will be 0.938 GeV. I want to make it TeV. TeV means is it not? That means this will be roughly say how much? 10 power minus 3 or 4 what? Okay, let us take it as 10 power minus 3 TeV. This will be the mass of the proton in TeV. And this is MA square. MA square means this will be 10 power minus 6 TeV square plus 10 power minus 6 TeV square because both are the protons plus 2 into 10 power minus 3 TeV into EA. Okay? And as you can see that in front of this 14 TeV, this 10 power minus 6 TeV square, 10 power minus 6 TeV square is a negligible quantity. That means my EA is 14 square. Roughly we can take it as 200 upon 2 into 10 power minus 3 TeV. That will be equal to 10 power 5 TeV. Instead of imparting one fellow 7 TeV of energy and another guy 7 TeV of energy, so that we have 14 TeV of center of mass energy, what we require in lab frame that my projectile should move with a kinetic energy of 10 power 5 trillion electron volts. Instead of 7 trillion electron volts, how much we require is 10 power 5 trillion electron volts. And therefore, in the next at least 500 years, it won't be possible to have energy of this much order. Okay? But one thing you must know, that whatever observations have been made at LSC in the last or more than 10 years, for more than 10 years, the same we could obtain had we this energy available in the laboratory frame. Therefore, observables, the observations they don't change whether you are performing the experiment in lab frame or you are performing the experiment in the center of mass frame. But what happens when you want to see exotic particles, when you want to see new particles, when you want to have the observation of heavier particles? Like, for example, one of the important goals of LSC was to see the Higgs boson, and Higgs had a mass of around 125 JeV. Now these are very massive particles, or top quark that has the mass of 170 JeV, or other similar kind of particles. When you have heavy particles, when you want to see new particles, when you want to see exotic particles, then you perform experiment in center of mass frame. But center of mass frame experiment is something like you are colliding, say, two clay balls from the opposite direction. Now in that clay ball, I have mixed many smaller particles. I have pink particle, I have yellow particle, I have green particle, I have gray particle, I have white particle. And that means, and all these particles correspond to a different particle. One is pion, another is kaon, one is electron, another is proton, one is positron, and all that. That means I have two balls of clays and I am colliding these two. Now when this consists of, when we are sure that many particles we can have in the final state, therefore when they will collide, what will happen? You will have a single system with loss of energy, and this clay will move in all the directions. And with this much of energy, you don't know whether a Higgs will come here, or whether X particle will come here, or Y will come here, or Z will come here, or Higgs will come here, or Z will come here, and so on. Therefore, what you do, you try to say this is a tennis ball. Then you try to cover this tennis ball by a football. And that football is the detector. That you place so many detectors around it to have a glimpse of Higgs. Therefore, Higgs was a rare event. Therefore, they had many detectors which were sensitive to the detection of Higgs particle, like CMS detector or Alice detector. Similarly, if you want to see quark-gluon plasma, in which Aligarh group is also involved, experimental group, the Alice experiment is there. Therefore, there are different observations which are taking place at LSC, but these observations are of different nature. The particles which are getting emitted are of different nature, and they have different detection capabilities, they have different detection sign. Therefore, you place different detectors to cover the place where the actual event is taking place. Therefore, in colliding beam experiment, we spend lot of money in building up the detector. Lot of money, and that is why these collaborations are huge. For example, in CMS, 1,500 people are involved, more than 20 countries. Similarly for Alice, for Atlas, and so on. Why so many countries? Why so many people? Because you need huge detectors, number one, where the cost is very high. Therefore, countries are sharing this cost. Number two, these events are rare. Therefore, you have to analyze all the events which are coming out before you make a decision that the event which we have observed is the event corresponding to a particular particle. Okay, the same was true for the Higgs. First, the analysis were made for many years, and then only it was concluded that they have observed Higgs. And that is why in these experiments, trillions and trillions of data that come out, and you have to analyze those data, and therefore you divide the work that, okay, 10% of the data in would be analyzed by Indian group, 10% by the German group, 5% by the smaller countries which are participating, and so on. And that is why there are large number of groups. There are 1,500 or 1,600 people involved in each detector. CMS is a separate experiment, Atlas is a separate experiment, Alice is the separate experiment, and so on. That means almost 10,000 people are involved at LSC as engineers, as scientists, and all that, so that they would be able to observe such kind of events, rare events, exotic events, new particles, and all that. And why this was not possible for the lab experiment? Because the energy that was desired when one has to sit at rest is 10 power 5 trillion electron volts, and that is a humongous amount of energy which is we cannot achieve in the next 500 to 800 years. But still, lots of experiments are being performed in the low energy region in the laboratory frame, because in the laboratory frame most of the events takes place in the forward direction. That means you have to place detectors only in the forward direction, and that means the cost of the detector becomes very small. Therefore, if you want to observe a particular type of event, if you want to observe a particular reaction, if you want to observe the nature of electrons coming out in this process, in electron proton scattering, then you perform experiment in the laboratory frame. Therefore, there is advantage and disadvantage of both laboratory frame and center of mass frame. And for center of mass frame, the advantage is that you have to if you want to see exotic particles, new particles, rare events, and all that, you need center of mass experiment. But the cost is you have to spend lot of money in detectors. You have to have lots of people to analyze the event. While in the laboratory experiment, you cannot presently go to trillion electron volts of energy, because the energy that would be required for the projectile would be very, very high, and you don't have accelerators to cater that. But if you want to study particular event, a specific reaction, and all that, then you have to spend less on the detectors, okay, and you can study in a better way a particular reaction. Therefore, this is the advantage and disadvantage over lab experiment and center of mass experiment. Now, still I have not started cross section. Tomorrow I will start with the threshold energy of a reaction, and then I will come to the understanding of cross section.
Excuse me, sir.
One second. And what is important, that these 3-4 lectures which I am spending starting from today, they are not given in the books, and therefore try to understand these concepts. These concepts are very important in nuclear physics and particle physics. Centimeter square means in an area over this, if we suppose I have got only one target particle, then if I have got only one projectile, then I will have to try 10 power 40 times to have a single reaction. Or if I place till about 40 particles in this area, then there will be the probability of interaction will be 1. And that concept is a bit tricky. That I will do. Let me tell you that on Thursday, I will be able to convince you that what is the cross section, how you can visualize the scattering, and what is the concept involved in all these lab and